basic framework for understanding the electronic structure. And this is something that a lot of us, we keep on taking a look at the band dispersions and the DOS, and sometimes we miss quite a lot of information in this band dispersion. So this is the approach that has been taken by the famous Professor Roald Hoffman, and of course other people also. But this is the approach to understand the band structures and the electronic structures of materials. So I will go to a point from where I think some of you might have seen this approach earlier. Most of us actually look at the k-space formalism, and we do not look at the orbital picture. So for some, it will be new, and by the end of it, I think end of 1 hour or 50 minutes, whatever I have, I think you should be able to predict some of these band structures. Okay, so now what we'll do is we will start with simple atoms, or molecules, if you want to call, uh, and then we'll bring these atoms or molecules close together. The simplest of them, which you see on the top, is the hydrogen atom chain, a linear chain of hydrogen atoms. Okay, and then you can perhaps take a look at the second example where you have conjugated double bonds. So a linear chain of conjugated double bonds like butadiene, hexatriene, octaftetraene, so on and so forth. Or you could even take any of these square planar complexes and them stack. These are all molecular complexes, remember, right? The square planar. And then I stack them together and make a solid out of it. So these are the kind of approach that I'm going to take over here and try to understand how exactly it leads to the formation of bands, how I can explain myself, or how I can visualize these band dispersions. Yes, of course, some of these are very hypothetical systems. The moment you look at a chain of hydrogen atoms, you'll shout at me and say that, look, this does not exist. And if anything that would exist, it would be H2 molecules, right? And they would immediately separate into hydrogen. Uh, Framework, and then see what exists and what does not exist. Okay, because the same framework will be used for things that actually do exist. So if I think of just hydrogen, then what you see over here, and let me also get this pointer, it might be helpful. So what you see over here is the hydrogen molecule, and this is called the highest occupied molecular orbital, and that's your lowest unoccupied molecular orbital. And these terms are reserved for the molecules. Uh, the moment you come to solid, you start calling those things as valence band, the top of valence band, and the bottom of conduction band, but we are still not formed any bands. So this is your highest occupied molecular orbital. And if I'm just looking at the 1s orbitals, then this is a plus plus combination, that's a plus minus combination. All right. Let's go on from a dimer to a trimer. So three hydrogen atoms. And take a look at this trimeric form and what are the possibilities. Of course, the lowest, the most stable one happens to be all bonding combination. And then we have You see, this is, so one of those is minus minus, and this is plus, and the other combination. So one has to resort to some symmetry also to work out all these combinations, which I'll skip for the moment. And then you have a plus minus and a zero combination over here, and both of these are of the same energy. Okay, if you look very carefully, although there's no attempt that has been made to make things very quantitative, but the size of these circle is smaller than the size of this circle, indicating that the coefficient of the linear, so these are all linear combination of atomic orbitals, right? And the coefficient that is given to this particular atomic orbital is much smaller than the coefficient that is given over there. Anyway, uh, that is just a side apart, but one should understand that these are essentially they are not always the same. Hmm. Okay, now we go to a four-membered cycle square, and so you see we have the highest occupied molecular orbital. Okay, I'll not call this anymore the highest occupied because we can have occupation over here also. Okay, I'll say this is the all bonding combination, and this is the all anti-bonding combination on top. And in between, you have something which is slightly bonding, slightly anti-bonding. We go to the five-membered cycle, and you see one, two, two. Okay. Then you have the six-membered one, two, two, one. There's a pattern that's emerging also. Okay. Always the lowest one is all bonding. And all bonding, there's only one way of having this all bonding. So the lowest lying molecular orbital, it's always one. Okay, and then you always have in pairs. Huh? One, then two, one, two, one, one, two, two, one, two, two, one. So keep on increasing. So you have one, two, 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 all the way till you find the completely anti-bonding. So this is a chain of, well, I can't count, but maybe 20 or 30 atoms, whatever. Just think that it's a chain which has got many, many atoms. Hmm. And that's the all bonding combination. All, so we, the way it's depicted, all shades are supposed to be plus, or you can take it the other way around. The unshadeds are all plus. It doesn't matter. So here you have plus minus, alternatingly plus minus. That's the maximum anti-bonding combination that can be, right? We cannot have anything more anti-bonding than that. So that's the top of the band. And in between, you have all these various possibilities. Okay. So now we see that as we are going from molecule towards a large chain, let's make it almost an infinite chain, then we start to see that there's a development of bands. And this is where we'll see that how we can address these bands. And to address these bands, you, a lot of you are physicists over here and are well familiar with all these block functions. But I'll not go into those details of the block functions, but except for the fact that I'll just say, okay, the wave function. So my atomic orbitals are chi0, chi1, chi2, chi3, chi4, so on and so forth. So all these hydrogen atoms, they are separated by a space A. Okay, that's my lattice spacing. And the molecular orbital psi of k is given as a linear combination of chi0 plus chi1 plus, and the coefficient of this linear combination is nothing but the block coefficient, e to the power I k n a. That's what we are claiming over here. Okay, k is my wave vector, n is a number, okay, which represents the, well, it can be the index of of the atom or the atomic orbital, as you wish to say. Okay, A happens to be my lattice spacing. So if you look on the right over here, so K is equal to 0. If I put K is equal to 0, then of course this fellow vanishes, just goes to 1. And all I have is uh, chi 0 plus chi 1 plus chi 2 plus chi 3, the complete bonding combination. So what we are looking at now is an infinite chain. Okay. And that infinite chain has been approximated as this big circle. This one could always think of the Born Karman boundary conditions also, but we will not have to worry about that. So this is a large chain. Okay. All right. Put the value of k is equal to pi by a, and let's take the molecular orbital psi of pi by a. And so I put these values over here, pi by a, n a. Okay, so that's pi I n. And for every value of n, I know it goes as -1 or +1. So chi 0 minus chi 1 plus chi 2 minus chi 3 plus so on and so forth. So it's plus, minus, plus, minus. And that we've already seen is the most anti-bonding combination, right? So if I say this is the lowest energy possible, then of course this is the highest energy possible. And the rest, everything that lies between 0 to pi by a, the energy of those particular molecular orbitals are going to lie between these two energies. Okay. So the highest energy orbital and the lowest energy orbital. So it will form a band, because this is, if I'm going to take this as infinity, then k, it's all infinite. We have lots and lots of these values, and they are continuous, or if you really want to be very accurate, then quasi continuous. So anyway, continuous bands doesn't matter for our discussion. Highest energy k is equal to pi by a, lowest energy k is equal to 0, and in between all the energies are there. So that's how you also depict a band. Now you would like to depict a dispersion. Okay. So energy at k is equal to 0 is the lowest energy. Energy at k is equal to pi by a is the highest energy. I invite all of you to calculate for any other value of k lying between 0 and pi by a, and see for yourself. Well, one doesn't need to verify, because you're looking at the two extreme limits. So everything lies between this. And if you do this calculation slowly for each and every value of k, then this is the smooth function that you will recover. Okay. So that's your chain of hydrogen atoms, and I have described those using the 1s orbitals. And that's my band dispersion going from 0 to pi by. So this is my one-dimensional chain. All right. Uh, what you're also sometimes looking when you're looking at the dispersions, you're looking that some dispersions are really, really wide, whereas some of them happen to be narrow. Okay. So one of the reasons is, look, it depends on how much the overlap is. Okay. The overlap between the two atoms, okay, or the two orbitals, the, the neighboring orbitals. So at 3 angstroms, so this is hydrogen calculation, uh, separation at 3 angstroms, 2 angstroms, and 1 angstrom. Well, the closer you get, you're getting, unless you get in the repulsive regime, you're getting more and more overlap, and therefore this dispersion, that is the difference in energy between the all bonding combination and the all anti-bonding combination, that is low, When you your atoms are far apart, of course they are not interacting, so why should there be a dispersion? As the atoms come closer, 2 angstrom, this dispersion increases. As it comes even closer, 1 angstroms, which is very close actually, so this dispersion is really really high. Okay. Remember, this is what tells you uh, the stabilization. Okay, Coulomb and exchange integral and the overlap integral in the bottom. If you look at the center of the band, that is where your atomic orbital is. This always reminds you that the anti-bonding orbital is more destabilized than the bonding orbital is stabilized, right? All right. Now, always you've not seen bands which are running from 0 to pi by a in the direction that we saw earlier. Yeah, not in this direction. But in a number of cases, you also see that they are running downwards. So, how exactly? What governs how they run? What governs is that look at the atomic orbitals. Okay. So right now, we took the example of 1s orbitals, which are spherically symmetric. And when they were spherically symmetric, then they were running from 0 to pi by a in the up direction. But take a look at p orbitals. Now, what should I call it? Pz, let's say. Let's say that this direction is z. Okay. And now, if I just use the linear combination with the positive sign, that is k is equal to 0, then all of these are anti-bonding combinations, and which means this is the highest energy molecular orbital or band. This is the lowest energy when I have plus minus combination. You can take a look at these orbitals. So this would be plus, that remains same. Minus, I would just reverse the sign. And then these two would form the bonding combination. These two would form the bonding combination. The node, of course, is there in these. So this would be the lowest energy combination. That would be the highest energy combination. In this case, they are running from up to down. Okay. Now you are armed to a great extent. And now we'll just solve one problem, and that is a problem of these platinum complexes. Okay. So we'll take the ligand as just a hydrogen orbital. We don't have to worry too much about the ligand. But look at these complexes. Okay. Um, and let's not worry too much about either they are staggered in the case above, or they are eclipsed in the case below. So if they are eclipsed, then the cell length doubles, the unit cell doubles up. So either ways, but what is happening is that, you know, before I go into anything else, so this is what the ligands are, and these normally the ligands happen to have a lower energy compared to the metal. So the d and s and p orbitals of platinum, and the most likely s orbitals of the ligands, or sp hybrids of the ligands, whatever. We are not really interested in that. Um, they are slightly lower in energy. They are more electronegative ligands, so they have to be lower in energy. And they interact with all of them, and they form the molecular orbitals. So right now I'm just talking of one PTL4, and this is dominated by the ligands. Here, what exactly interacts? X, Y, X, Z, and Y, Z, these d orbitals, they hardly interact. What interacts is z square. What interacts maximum is x square minus y square. Okay. So these are the things, or not z square actually, it should be xz. So some mistake is there. And x square minus y square. And so p orbital also of the platinum. Hardly Z would be interacting, hardly the rest of them would, you know, because Z happens to be out of the plane and the ligands are in the XY plane. So that's what these things are. Okay. Now, what I have to worry about is when I stack them together. The moment I stack them together, the stacking direction will be the Z direction. Okay. So all of those orbitals, the d orbitals that are pointing in the Z directions are going to interact with each other, right? And if I think of that, then I can predict, or I can make an educated guess of the band structure. Okay. So before I go into the band structure, let me also tell you that you've seen the dispersion, and the integration of that happens to be your DOS. So DOS, the density of states of E times D, is the number of levels between E and E plus D. And you can also define it with the volume, but don't worry about that for the moment. Okay. Now, if you look at the monomer, so on the left here, this is the monomer that we just saw. Okay. So, what do you expect the DOS to be? These are your ligand levels, right? And these are not going to interact, right? They are in the XY plane. So, if I bring two platinum L4 complexes or H4, whatever you want to call them, and bring them closer, then whatever is the interaction in the XY plane, that's hardly going to hardly going to get manifested. So this almost remains like a very localized kind of DOS. It, it doesn't interact. If it doesn't interact, what we had seen earlier was, in the case of 3 angstroms hydrogen, it's going to be a flat band. So if I look at the bands also, okay, over here the bands are not even shown. We don't even need to worry about that. So let's go to the next one. Now, some of these are not going to interact. Why? Because the ligands, the d orbitals, only those d orbitals that point along the z direction are the ones that are going to interact. So z square would interact the most. So that would be a band which is gotten more dispersed, right? It's not so flat. XY, being in the XY plane, doesn't interact, so it's a very flat band. And XZ or YZ also has some component in the along the Z direction, so that also interacts a bit. And if I look at the DOS, I I look at the DOS. These delta pi and sigma are nothing but the bonds. Okay, sigma bond, pi bonding, and delta bonding. Don't worry about that. But sigma is head on, and that interacts the most. So I'll have my dispersion, which is maximum for Z square, less for x, z, y, z, least for y, z. Okay. Likewise, I'll have least for x square minus y square, highest for z. And the energy order is also going to be more or less in this range. Okay. Likewise, the DOS also. So I can, although I cannot do things quantitatively, but qualitatively, I knew what is my electronic structure of the basic building unit. Okay. And I deliberately took an example which was more look, or at least looks more complicated. So I know what is the electronic structure of the basic building unit. And this is something we can very easily work out with just the knowledge of some electronegativity and bonding. I can predict the DOS of the polymer, of the chain that has come. I can do similar things with solids. Okay, and I'll give you some take-home exercises where you can work out all of these things. I can predict the density of states. I can also see how my uh, mm, sorry, these band structures run. Okay, so this is going to be a very broad wide band. Ah, so if I look at what the orbital overlaps are, then I can also tell that, okay, whether these are going to run up or down. So k is equal to 0 is plus minus, k is equal to pi by a. So for the z orbital, pz, this is your pz orbital. That's your xy, xz, and z square orbital. So z square, it's going to run up. PZ, we've already seen it's already running down. You can make out for the rest of them. But once you've made out all of these, you know that Z square is the one that was very broad. XY was the one that was sharp. It wasn't very flat, right? And X, Z, and YZ, which are running from up to down, uh, they were broader than xy but less than z square. And also z was again very broad, it's going out of the scale. And this is your x square minus y square, which is got to be flat. You can make, you will not be able to make this unless you know some bit of symmetry that they falls at the same point. Yes, but you can do a lot of qualitative prediction, and this is the calculated band dispersion for the PTH4 chain. Okay, so qualitatively, very much in agreement. Quantitatively, of course, you get the numbers. You can't do a qualitative hand waving argument, but one can get to understand what the band dispersions are, even without having to do the calculations. Okay. So far, so good, and everything seems to be very simple. But then let's make more dimensions. And, since we are going to deal with two-dimensional materials, let's come to two dimensions over here. Okay. So A1 and A2, this is your two-dimensional net. You can take this to be a square or rectangle, whatever, doesn't matter. If it's a square, then also I've shown the Brillouin zone over here. Uh, that's the X point, that's the M point, that's the gamma. The gamma point is nothing but k is equal to 0, k is equal to 0. Now we start naming these points also, and that's what you see in the band dispersions, right? Okay, k is equal to 0, k is equal to 0, and I take s orbitals. And then you see all of them, these are all bonding orbitals. Okay, now I will take the next one, which is kx is equal to pi by 2a and ky is equal to 0. So along the ky direction, everything is bonding. Okay. Around the kx direction, it's got to be anti-bonding. Okay. All right. Pi by 2a, by the way. In fact, I should have taken this first because that's the correct anti-bonding sequence. This is the x point, and so kx is equal to pi by a plus minus, that's pi by 2a. So you've just doubled the uh, reciprocal lattice point. Okay, you can take other combinations. So pi by 2a, kx and ky, so that's your m point, and this is your, so pi by a is your m point, and pi by 2a is somewhere over there. Okay, so you know this fellow and this fellow are kind of related by symmetry. This and this are related by symmetry. So because it's a square lattice, we've taken it for simplicity. Uh, and then I wish to plot these various directions. Okay, so gamma to x, now gamma is the lowest energy point, and x is a point where you have, well, what you have is bonding along one direction, anti-bonding along the other direction. If you look at M, it's bonding along, sorry, anti-bonding along both directions. So M is more anti-bonding than X. both of them are x points. Yeah, x or y happen to be x points for the square lattice. So gamma to x, it's going to run up. X to m, again, it's going to run up. And if you take gamma to m or m to gamma, then you're going to run down. And now you see that, you've made one dispersion, and this is related to the s orbitals of your hydrogen atoms. This is just a hydrogen atom net that we saw. And you've got one dispersion curve. Now, what you need to do is to worry about including more orbitals. You know that in the dispersions, it's not just one orbital, but a lot of orbitals are involved. Ah, and all of these are going to interact with each other. Right now, I've not made them interact. This is your px. How does how do the px orbitals interact amongst each other? Okay, so if I look at the gamma point, then px or py, they are very highly antibonding, right? Um, Along this direction, but bonding along this direction. Look at this one, the x point, your px is bonding along this direction and bonding along this direction as well. And that's why it's also labeled as sigma pi. It's a pi orbital along the x direction and sigma orbital along this particular direction. Okay. And sigma star, this is the antibonding of pi interaction. Likewise, you have sigma star, well, antibonding in this direction, and pi star, antibonding in this direction. So you need to differentiate between x and y now because you have the px and py orbitals. So that does not allow for the square symmetry, or even if it's symmetrical otherwise. And then you have sigma and pi star, which is m. Now you start plotting all of these band dispersions, how they run. Okay. So if you start plotting all of them, then you'll get a feel of how, on top of this, more dispersions will come. Okay. And one can get the entire band structure of the hydrogen net. Okay. This I have left as an exercise for you. But if you think of, going from uh, gamma to x, well, first thing is that this is your s orbital. So s orbital, one s orbital, and this is the lowest in energy. Okay, 2s, then 2p. So 2s is also going to be of the similar kind. 2p would come at a higher energy. And if I have to make them, if I have to see how it runs from gamma to x, then I know this is going from sigma star to sigma, pi to pi. Okay. So if I look at the px orbital, then it's going from a high energy orbital, which is sigma star, towards sigma. So from high to low, that's going to run down. And if I look at the py, then then it's going from pi to pi star. Okay. And pi is a lower energy orbital. Well, sigma star to sigma star, it's the same, but pi to pi star. So pi is a lower, but pi happens to be, not such a strong interaction, which is a lateral interaction compared to the sigma, which is a head-on interaction. So the width of the band that is running for px is going to be much larger when I go from gamma to x, is going to be much larger than the width of the band that runs for py, because that is from pi to pi star. Okay, but they are running in opposite directions. Okay, so I encourage that you make this entire band diagram and see how it comes about. Okay, so this is where I'll stop with the first part of the lecture, where I wanted to offer you another point of view for looking at the band dispersions and, you know try to also predict these band dispersions. So I'll stop here and then I'll go on to describe the research work that we do on transition metal dichalcogenides. So
Makes sense.
I'm open for questions or discussion.
Yeah. So I see is one. It is not question actually. Uh, from Dr. Prahlad Rao PB. He is not able to follow the discussion. In fact, this is very nice introduction. I could realize that the kx, ky, kz, all these in the physicist perception, we normally take them as numbers, but in fact, they are combinations of the orbitals.
Right,
So,
right.
so the uh, query is
Oh, some reference book. Okay. So as I said, this is an approach by Professor Roald Hoffman. So one could take a look at his landmark paper in 1985, I think, in Angawante Chemi. The entire description is given over there. Hoffman, Hoffman. And this is the famous Hoffman of the Woodward-Hoffman rules. So, yeah, there's people who are writing some. I'm listening to this first time, but I thought that there's a lot of physics crowd and they would be well aware of band dispersions. So I thought I'll give them this.
actually, they are all not physicists. Actually,
Not
they
physicists, not
are
okay.
mainly from engineering backgrounds,
Okay.
diverse background. So, although this was discussed earlier, but somehow he want a chemist's perspective of high symmetry points, kind of.
Sir, can you tell me why these are called? Because you see, the symmetry is high over there in these points. Links. I'm sorry, Anjan. I'll have to search. Maybe I'll share the link with Professor Manoj, and then he could. Uh, it's an Angawante Chemi paper.
Yes, sure. Uh, Along with the copy of the slides, we can share some study material so that
Sure, I have that. I have the paper downloaded with me, so I could share that also.
that will be perfect. So we'll share it with the participants
Sure, sure.
through Canvas.
Mm. This
So
is just the beginning because what I've shown is just understanding the band structures. Okay, and sometimes, especially for chemists and people who do not uh, study so much physics, it's a very difficult thing to understand the band structures. So this is an approach which I find that chemists can understand much easily because it's again just bringing the orbitals together, linear combination.
indeed, all this quantum material thing is reading the band structure carefully and band dispersions. They make
Right.
the material trivial to non-trivial, and there was lots of discussion on that. So
And
really important.
also one can if you just take the approach that is the normal thing, you do a calculation. Over here, you start to understand and appreciate the orbitals, and then you can do you can actually make out qualitatively. Okay, you can't do
Yeah.
it quantitatively, but qualitatively you can make out the band structure. You know, so for those who understood the topic, you're ready to take on any inorganic material, for example.
So, sir, normally we take a small break in between two
Yeah, yeah,
hours.
sure.
So, it's up to you actually, how you
No,
plan.
we can take a 10
Can
minutes
take a
break
break
and
right now, or we can break later also. Yeah.
yeah, we can take a 10 minutes break and then resume at 4 o'clock.
Yeah, perfect, sir. Thank you.
All right.
Yeah. Welcome back, sir. Can we start?
Thank you, thank you. Yeah, sure, sure, we should.
Okay, sir.
It's okay. Are there some more questions or nothing? So I will again share my screen. Okay, so this is more of the research part that we have to do with the transition metal dichalcogenides. Okay, and we've been working on these materials for the past almost 10 years now. Uh, and these are the people who've been involved: Shamim, Swati, Sahil, and Varsha, and various aspects of these materials. So that's my group over there. And I must thank the DST, DRDO, SERB, two of these companies, Marmon and Analinear, who also funded our research, because some of the research that we've been doing has some applications, and I'll come to that and I'll show you that. And the Central Research Facilities and the Sophisticated Analytical and Technical Help Institute, SATI, at IIT Delhi. Here we do a lot of measurements of our materials, and these are open for everybody, so like other central research facilities. My collaborators who help me a lot, Shashwata and Dibya Jyoti, who help with a lot of theoretical inputs, computational, and Pralay with a lot of TM expertise, and Praveen and Shashanka, who are very good at, they're very good electrochemists. Okay. So I'll not go with the contents. I'll just tell you something about uh, the 2D transition metal dichalcogenide nanosheets. And this work was started by Shamim in about 2016, as I mentioned earlier. So here we have transition metal dichalcogenide. Okay, so like MOS2 or MOSE2 or tungsten sulfide or tungsten selenide or niobium sulfide. So you take the periodic table and stare at the center of the periodic tables, the D block elements, and take some of them and mix with the chalcogens. A lot of them they form these transition metal dichalcogenides. Okay. In fact, uh, if you look at the structure over here, okay, let me again get the pointer. If you look at this structure, that's your metal atom, a metal ion in the center, and the red ones are the chalcogens. And if you look at the arrangement over here, the way these are arranged are in a trigonal prismatic coordination. So three at the top, three in the bottom, molybdenum in the center. And now what you can do is you can extend another molybdenum here, another sulfur here, another, or maybe extend molybdenum, sulfur, and keep on extending the same units uh, in these direction. Let's say this one direction and one direction coming out of the screen, and this is what you get. Okay, so in the center, all you have is molybdenum. On top, you have sulfur. On bottom, you have sulfur. So that's a molybdenum sulfide. That's the most studied material, by the way, molybdenum sulfide. And then, if you look at this, in between, you have a gap. And then you have another layer of molybdenum sulfide. Then you have a gap. And that is why these are your 2D materials, or they can be made to be. These are layered structures. Okay. So, layers of transition metal dichalcogenides, and how they are held together. Ah, if you look at the electronic structure, you'll see that there's an indirect band gap over there. And that indirect band gap is because of the fact that you have the sulfur debonding. Okay. and the sulfur p bonding also, they are involved in this in this gap between the layers. So d orbitals, they're bonding together. But if I actually exfoliate these materials, and exfoliation, you've heard of graphene, the Scotch tape method, simple. There's also possibility of chemical exfoliation. There's also possibility of just doing ultrasonication. So a lot of exfoliation methods are there. If you do that and you get one single monolayer, then there are no d bonds. Okay, and if there are no d bonds, those particular bands are absent completely. Okay, so what you have is all the top of the valence band and bottom of the conduction band, everything happens to be within the layer, and there happens to be an indirect to direct band gap crossover. Okay. The excitons are strongly bound in these materials because these excitons, they stay within the layer. It is, it costs energy to cross. huh? There's a lot of hopping energy. Mobility of charge carriers, again, if it is within the layers, it's got to be very high. And we can, because we can exfoliate, and we can do that contrarily. So we can also tune the energy band gap, and that tuning of the energy band gap is something like you've heard of in quantum dots. In quantum dots, what you see is as you reduce the size of the particle, the band gap keeps on increasing. And that one can explain very easily with a particle in a box like model, n square h square by 8 m l square, where L is the length of the box, right? The same model you can use, and you can tell that, look, if the length of the box, or in this case, the thickness, thickness of this. So as I keep on exfoliating, make it from multi layers to a single monolayer, I would increase the band gap of the material. The other good thing is that it has a very high specific surface area. If I actually exfoliate everything and make it a single monolayer, then everything is a surface, right? And because everything is a surface, and what you require for catalysis is you need sites on the surface, so you have very good catalytic activity also. So these materials happen to be useful for a lot of applications. One side you're looking at a lot of optoelectronic applications. At other side you're looking at surface related catalytic applications. So a lot of these things. By the way, this is not the only coordination, trigonal prismatic. You take this trigonal prism, okay, and rotate it. You rotate it by 60 degrees. Okay. Yeah, you rotate by 120, you get back the same thing. Rotate by 60 degrees. One of the triangles, let's say the triangle on top, the red one, the three red atoms on top, I just rotate that by 60 degrees, and what I get is an octahedral coordination. Okay. But the thing is, if you look at the trigonal prismatic chord, well, octahedral is something that everybody understands. And there's the T2G EG splitting. Okay. And T2G EG means that you have three electrons over there in T2G. Okay. Instead of three electrons, if you have two electrons, for example, in the case of molybdenum 4 plus, you have two electrons. So if you have just two electrons, then rather than the octahedral coordination, the trigonal prismatic is more favored, because in the trigonal prismatic, the ligand, the crystal field effect is such that you have two orbitals at the bottom, then one, then one, and then one. Okay. So these two orbitals in the bottom are occupied. Okay. The third electron is not there. But if you wanted to put a third electron in a trigonal prismatic, it would go to a higher energy level. And therefore, when you put a third electron, it crosses over and makes a octahedral coordination. That's what exactly happens if you take molybdenum sulfide and you exfoliate it chemically using lithium. Lithium can go within these layers. Okay, these are also very good as battery materials because they can intercalate lithium. So lithium atom, when it goes inside these materials, it gives off one electron. That one electron is the one that makes it go to the octahedral coordination and also makes the system metallic. Okay, so those things have been studied by people. So a lot of research has gone into all that. So there are various ways. So trigonal prismatic is one. Then we look at octahedral coordination. Okay, so Shamim is the one who actually started this work. Before Shamim, Razi was working on molybdenum sulfide, but we were just mechanically exfoliating them. So Shamim is the one who started with molybdenum selenide, and not much was done in molybdenum selenide. So he started working. He took some heptamolybdate, made the acetyl acetonate out of that, the molybdenum macaque. Acacs are usually very good precursor for any synthesis, especially if you want to decompose at high temperature, and that's how he does it. He takes this molybdenum macaque, takes a selenium precursor, polylamine is the solvent in which you dissolve some selenium. That's your selenium precursor. Heat it at Any better now? All right. Uh, Camera is also working. Yeah. Yeah. Now I'll share. Yes, yes, sir. I have to share the slides. Sure. So I think I was over here, and the slides are visible now.
Yes, sir. Slides are visible in full screen, perfectly fine.
Okay.
And you just started this slide that time.
Hmm. Okay. So I'll start with this. So what Shamim did was he started using this acetyl acetonate, so which are very good precursor for high temperature synthesis. And he took oleamine in selenium as the selenium precursor and heated the acac at roughly around 180 degrees and injected the selenium precursor. He got these molybdenum selenide nanosheets. Okay, these nanosheets, this is how they look like. Okay, but if you look at the nanosheets that are obtained by other methods like sonication or exfoliation, then you get very clean, very atomically flat like nanosheets. Okay, whether we do it or this is, of course, the great Novoslav's paper. So um, anybody, you look at them and you'll get very nice things. And this looks like a crumpled sheet of paper. What happens exactly is when you're using this high temperature colloidal synthesis method, then you get a lot of defects. Okay, so you get these defects which are absence of selenium, and because of that the molybdenum tries to attract the next nearest neighbor selenium and therefore folds in that, you know, kind of crumples like a sheet, if you see. So all of these 0.65 nanometer are interlayer spacing distances typically. Okay, and so what you see is that you have a lot of defects in this material, and then you're not very happy with the defects. But Shamim is always happy with whatever he gets, and he said if we have defects, then if you look at these edges, okay, these edges are unsatisfied valencies. And if you have unsatisfied valencies, then those are very good for catalytic activities. So the first catalytic activity that he planned was the electrocatalytic hydrogen evolution reaction. So all he did was he took a platinum electrode as a counter electrode and took a glassy carbon. On top of the glassy carbon, he put his material. The material is, added some carbon black and some Nafion binder. They are added to the material so that they stick, so are conductive in nature. And then you start applying a potential. Okay, some electrons over there. Now, if you just use platinum, okay, so platinum requires 0 volts. That is the definition of the standard hydrogen electrode. This is all done in acids, 1 molar acid condition. So platinum requires just, 0 volts. Ideally, but when you make a when you make a device, things are not ideal. So it requires, you know, up to about 0.1 volts, 100 millivolts or something. That is where it starts coming down. People always report the current densities of minus 10 milliamperes per cell. They will report the over potential at. So that's for platinum. All right. And also the slope of this curve, the inverse of the slope of this curve is known as the Tafel slope. Uh, the lower the value of this slope means the fast it comes down, which means at a smaller voltage, you can get higher currents. So that is about 38 millivolts, which is a pretty decent number for platinum, of course. So platinum happens to be the best material, no doubt. Now you take molybdenum selenide. That is molybdenum selenide, typically about almost 500 millivolts, and a Tafel slope of 110 millivolts per decade. Doesn't seem to be very nice. Also, the fact that, when you have this molybdenum selenide, this is something called the um, EIS spectroscopy, and this tells you that you have some resistance, okay, going from here to here, the electron going from here to here, and you have some capacitance and resistance for the electron going from the electrode through the material. Okay, so resistive path and capacitive path. And the smaller this semicircle, the smaller is so the sum of the capacitance and resistance. Okay, so then you've taken molybdenum, selenide, bulk material, and now you take six monolayers of this material. Immediately you see this overpotential has come down, the Tafel slope has reduced, this semicircle has become smaller, and that is because you see the electron has to jump across all these layers. In case of bulk material, it has to jump across many layers to reach the electrode, uh, to reach H2O from the electrode, and therefore it takes H plus and gives H2. In case of six monolayers, it has to jump only six monolayers. Okay. In case of a single monolayer, it doesn't have to jump. It has to flow only in the monolayer. Okay. And therefore, six monolayers is even better. Huh? It's even better. 54. This is also small. And if so, these are our first devices, right? So not very standardized. We just did for 10 hours and we quickly reported, okay, molybdenum selenide is also giving these kind of nice HER reactions. So we could do that. Well, this is how it goes. This is a very interesting thing. If you look at the catalyst surface, okay, then on the catalyst surface, you put one H plus, okay, and the electron comes from the battery, from the electrode, and it forms a H dot, so a hydrogen radical. Now, so you have this hydrogen, it has to react with another hydrogen to get H2. There are two possibilities. One is that another H plus comes and sticks to another site. The second possibility, so this is called the Tafel step. Second possibility is the Heroski step, that somehow the H plus finds this hydrogen, which is already sticking. Of course, this is a more challenging task to find this hydrogen. Whereas if you have another site, this can very easily come. If the site is close by, then this fellow can also take an electron, become a hydrogen radical. These two can combine, and hydrogen can come out. Whereas if somehow by chance this is found, then hydrogen can come out. So either ways, you can have hydrogen production, but this requires more challenge. So that is why the slope of this is is is, is not so steep, or the if you're going to larger values, which is the inverse of this slope, so then it becomes more challenging, and it's which means it's taking more of the Heroski mechanism rather than the Tafel mechanism. But the slope is coming down as you are reducing the number of monolayers, suggesting that it is moving towards the Tafel mechanism, and that is because you have created a lot of defect sites. These defect sites are the points where your H plus can go and sit down and then wait for an electron to come. Okay. If you do not have the defect sites, then it is likely that you have Heroski step. Okay. All right. So Shamim, after having completed this successfully, he said, "Okay, I want to go further with these transition metal dichalcogenides and make some heterostructures." So he said, "Fine, molybdenum selenide we have, and the first thing, if you want to make a heterostructure, even before you think of a functionality, what you have to think of is these A, B, C parameters. Okay. Now this is hexagonal, so one doesn't have to worry about C because C is the direction on which you normally grow. Okay. So one has to worry about the lateral AB direction dimensions. Okay. So if this is 0.329 and 0.379, you can do this quick calculation and see this is about 7% lattice mismatch. Okay. Now 7% lattice mismatch is not very high. I would say, well, some of the people who do epitaxy and all would say it's high, but for a colloidal synthesis, it's not very high. Okay. It's doable. So what he does is he makes the defect rich molybdenum selenide and then puts dodecanethiol. Now, dodecanethiol is a 10 carbon chain, 12 carbon chain, sorry, with a thiol SH group. Now, all these sites are selenium, devoid of selenium. So molybdenum is really hungry for filling up these sites with selenium or something which is equivalent to selenium, which is sulfur. So these sulfur atoms go and attach over there. If you look at the Raman spectrum, if you look at pure molybdenum selenide, then you have this is the A1G peak, this is the E2G peak, and in between, what you see is the peak because of defects. Okay. If you do not have defects, you don't see this peak. In fact, when you passivate the defects with DDT, this peak also diminishes. Okay. So you can see these are typically one monolayer, all of these. So it's deposited on gallium arsenide and then an AFM has been conducted. So 0.65 nanometers is typically one monolayer. So this is almost the same. Uh, where are we? Yeah. So this is the kind of thing. You have dodecanthiol and now you throw in cuprous iodide on top of this. The copper has a very good affinity for the chalcogens. So immediately it forms cuprous sulfide islands on top of this. This is attested by all the XRD. And if you look at the TEM, this is your molybdenum selenide. And if you just make cuprous sulfide, then you get these hexagons. But once you make them with molybdenum selenide, then you start forming these hexagons on top of molybdenum selenide. We wash these several times to make sure that they are not just physically attached. Huh? They're attached to. They're chemically attached over here. And also, if you do the XPS, then you'll see that molybdenum. There are two species. One bonded to selenium, which is the larger chunk, and a bit that is bonded to sulfur. Okay, the higher electronegative sulfur, so therefore higher binding energy. Selenium is only one species because it's bonded only to molybdenum, not to copper. Okay, that's the model also. That's what it. Copper is the one that reacted with sulfur and is bonded only to sulfur, so just one species. But sulfur is bonded to both molybdenum, the smaller one, and also to copper, the larger contribution. Also, some amount of sulfur gets oxidized on the surface, so sulfate is formed. Acha, remember one thing: copper, there is only one species. Okay. Now, Shashwata and his team, Pooja Basera, they do these calculations for us. And they say that, look, what you have is a type 2 kind of a heterostructure. Okay. Now, the type 2 kind of heterostructure is like this. So, this is your conduction band, that's your valence band for copper sulfide. That's the band gap for molybdenum selenide. So if you excite these materials or you have electrons and holes in the materials, then the electrons in the conduction band would like to flow towards molybdenum and the holes in the valence band would love to go towards cuprous sulfide. So there's a built-in electric field, okay, in the material already. And this is the type 2 kind of material. So there's a flow of charge also that is naturally decided in what direction it will go. So there's a charge separation, natural charge separation. So charge separation says that look, use these materials for any of those applications like photocatalysis, like photovoltaics, uh, or easier photoconductivity. So what you do, you take a p-type silicon and put your material on top, put some gold pads on top, shine some light, and see what the conductivity is in the absence and presence of light. So if you take molybdenum selenide without any thiol, okay, just the one with a lot of defects, you take that, and that's your dark curve, and the bright curve is also very close by. There's about 27-fold enhancement in the uh, bright to dark ratio. If you put some thiol, what you've done is essentially passivated the defects. If you passivate the defects, then your charge carriers can move through more easily. Okay, and therefore, this is your dark current. The dark current is almost similar. That's your bright. Okay, I think that 100-fold increase. But if you take molybdenum selenide cuprous sulfide, then you have a built-in electric field. Also, you have passivation. So your dark current increases, which is not too great. Okay, but your bright current shoots up. There's 3,700 folds. Okay, so this becomes a very good photo detector. In fact, since we also biased it, we put some amount of N molybdenum selenide, and there's a P-type silicon. So you see, this is not just a photo detector. It's these are measurements in reverse bias, and in so this is more of a photodiode. Okay, because of the bias that we have created, and you can see that you can measure these things again and again. That's the energetic diagram. I'll rather skip that for the moment. But we then, we have collaborators in SSPL, and we took their help to make some very good devices with the same materials. They did it on gallium arsenide. And if you look at this is your dark current, which is 10 to the power minus 8. And that's your bright current, 10 to the power minus 3. So that's almost 10 to the power 5, 1 lakh fold enhancement in the bright to dark current. So one can make very good photo detectors or photodiodes actually. Yeah, look, this is also diode like behavior. All right, this is good because uh, we could also make photo detectors using the transition metal dichalcogenides. But Shamim was still working with these hydrogen evolution reaction, and then looking at Shashwata's calculations, mm, he said, let's align the energy levels of the normal hydrogen electrode along with the bandages. So once he did that, he saw that very small voltage is required to actually get the holes out of cuprous sulfide or pump in electrons into molybdenum selenide. So if you can get out holes, then what you can do is you can do an oxygen evolution reaction, and if you can throw in electrons, then that's good for the hydrogen evolution reaction. So he carried out the oxygen evolution reaction then using these materials. So the device is the same that I showed you earlier. Yeah? Just take one glassy carbon and put your material on top. Uh, except that there are some more nitty-gritties. It's a 3 electrode measurement because you want to measure current differently and potential apply the potential differently and do not want them to interfere. But otherwise, it's the same thing. Now, look at this pink curve. That is iridium oxide. That is the one that is being used commercially in the electrolyzers these days. And look at this blue material from Shamin. You know, it starts late, but then at about 1.6 volts, it overtakes iridium oxide. Now, if you're going to work with these materials, you're not going to work at small uh, current densities, you typically work at a few hundred milliamperes per centimeter square, huh? At least 500 milliamps to 1 ampere, something of that range. So you will have much better currents at lower voltages for Shamim's material. And you can understand, again, you can look at these EIS spectra and you can understand the same things that we were discussing earlier. Okay. I'll not go into those details again, but look at the mechanism over here. Now, to look at the mechanism, what he did was he scraped off some material after doing the reaction. Now, copper, remember, it had only one component earlier. Now it has two components. Also, you see these peaks, these are tests for the formation of copper 2 plus. Earlier, you didn't have these because you had only copper 1 plus. These are your satellite shake-up peaks. Okay, so you have copper 1 and copper 2, both of them now coming in, and almost equal intensity. So, what is happening is that your catalyst has both copper 1 and copper 2 sites. Copper 2 is bound with an OH minus. Copper 1 is free. OH minus comes in. Another OH minus comes in, abstracts the proton. Another OH minus comes in, sticks over there. Another OH minus abstracts the proton. Another OH minus breaks off this O2. Recur same catalyst. O2 evolution step. Okay. So what Shamim made was MoSe2 CO2S. Okay. After electrocatalysis, also look, the XRD pattern doesn't change. The TM doesn't change. But on the surface, these are the things that change. So after electrocatalysis or during electrocatalysis, your material is changing a bit. So what Shamim made was a pre-catalyst. Huh? After going through a few steps of the electrolysis steps, okay, it has converted into the real catalysis, which is a mixture of copper 1 and copper 2. Okay. Also, this material is pretty good for hydrogen evolution. So what Shamim made was on one side of the cell, hydrogen evolution, on other side as oxygen. So this is good for splitting water. Okay. So you can you can actually take water, put in some so these are all done under alkaline conditions. Put it under alkaline conditions, generate oxygen and generate hydrogen on the other end. Okay. All right. That was the story with cuprous sulfide. Shamim also tried to make some more heterostructures. He started making cubic heterostructures, and later on Shashwata and Pooja again did some calculations and showed that these are also type 2 of kind of heterostructures. So again, you have a charge separation over there. But perovskites are cubic and these are hexagonal. And one doesn't talk about lattice matches over there. So he tried to make them, and these things used to just disintegrate. It used to form something else. I'll come to that. But then he said, okay, let me take this molybdenum selenide. Let me take a thiol molecule, which is 4-amino-thiophenol. So you have a phenol molecule over here, benzene ring. So it'll allow for charge migration. And the thiol molecule is going to go and stick over there. Okay. So this is going to stick over there. The amino group is free. Now, it so happens that cesium lead bromide is also passivated by an amine, like oleamine, for example. Now, oleamine is olam. Huh? That is used most commonly because it's a liquid at room temperature. And the boiling point is about 360 degrees. So you can use this, no problem. Instead of oleamine, this amine goes and sticks over there. Okay. And the perovskite nanoparticles, they come and stick on top of this. So this is how it results. Okay. Uh, Doing these calculations, what Shashwata also realized was that the density of states is not zero for four. So, it's very small, but not zero. So the charge gets carried across. Okay. So there is separation of charges from molybdenum selenide um, to the perovskite, and therefore one has this type 2 kind of heterostructures and the built-in electric field. And the very interesting thing, so I have put the previous results also over here, and now if you look at this, this result is almost similar to molybdenum selenide cuprous sulfide. This was the one, but it's very flat. Mm. The dark current has come down a bit. I think this is about 20,000 fold enhancement. But the very interesting part is look at 0 volts. At 0 volts also, you get a photocurrent, which means you're looking at a photovoltaic effect. Okay, since you're getting photocurrent at 0 volts, and that is because the perovskites are well-known photovoltaic materials. Cesium lead iodide, in particular, has been used for a lot of the perovskite-based photovoltaics systems. Okay, and that is where this research led us to later on. But we also made some molybdenum selenide cobalt sulfide nanoheterostructures with Sahil, and he showed that these were very good capacitors, or rather supercapacitors. Now, I don't think I should be going into great details over here, but if you look at these curves, the more square they are, the more the more good they are as capacitors. So look at these squares, okay, and these are your um, GCDs, okay, the discharge curves. So if you charge, okay, galvanostatic charge discharge, so you charge that at 1 ampere per gram, and then you leave it, slowly allow it to discharge. So at the same rate, 1 ampere per gram. So it takes about 800 seconds. And we could do this repetitively for about 10,000 cycles. So these are very good supercapacitor materials. You can, you know, 800 seconds is typically about 15, 900 seconds is 15 minutes, right? So you can run your buses on these kind of supercapacitors. You really don't need batteries for storage. You charge them. You can charge them very fast. You see, some of these charges are very, very fast. Okay, 1 ampere, 15 ampere per gram. You can charge them to this capacity and then discharge them slowly. So you can do all these kind of activities very fast. For example, running buses. You charge them within 2 seconds, 5 seconds, and then run them for 10 minutes. Then you go to the next station and charge them. All right. So these are supercapacitor devices, which are very easy to make, very easy to fabricate, and this was with the help of Sasanka and his student Javed, which we could do. So there's a lot of collaborations that are involved. Then, of course, Varsha has been working on niobium sulfite selenides, and these are very interesting for water splitting applications. In this case, hydrogen evolution. What we learned over there was that uh, you know the most active part happens to be within the two layers, okay, not outside. So here, this is the vacant site of selenium in between the layers, which gives you most activity. We don't understand why, but that is what Dibyajyoti and student Ankita, they tell us that, look, this is the best site for the hydrogen evolution. Also, we made some of these um, cobalt-based supercapacitors using these transition metal dichal. So the transition metal dichalcogenides are a very nice platform for your thin sheets, where you also can allow your charge movement. So you can use them for various applications. Okay. So this is exactly what I was telling you. in between in the selenium rays. We don't understand why, but the calculations show this. Okay. Uh, then you can make heterostructures with nickel selenide and go on with even better results for hydrogen evolution. Or you could also, change instead of oxygen evolution, which costs 1.23 volts, you could go over to urea. You take urea oxidation reaction, and that costs only 0.39 volts. So the thermodynamics is much, much better. And you see that urea oxidation, the pink curve, okay, happens much faster than the OER, the green curve. So one can club urea oxidation. One can club a lot of other reactions which are useful along with hydrogen evolution. So you don't have to just be limited to oxygen evolution. So breaking water seems to be the natural thing and easy thing, but it takes more energy. Okay. All right. So this is where what happened when Shamim was trying to make those heterostructures of perovskite and the molybdenum selenide. So, this is your molybdenum selenide nanosheets. And the moment he would put some cesium oleate, it started to break like this. You see these molybdenum selenide sheets start to break like this. And what it does is to form uh, lead selenide nanocrystals. Okay. So Swati, then she took over this project and said, okay, we form these lead selenide nanocrystals. Uh, Let me also make lead selenide nanocrystals using the standard method. Okay. One is using the molybdenum selenide and one is just using the selenium precursor. And then we will put some cesium oleate. Okay. So you make the lead selenide and then put cesium oleate and let's see what happens. And the moment she put cesium oleate, then without lead, of course, without selenium, of course, you just get cesium lead bromide, CPB. With some molybdenum selenide, you get cesium lead bromide, but there are small amounts of selenium there. And with the selenium precursor, you get larger amounts of selenium. In fact, you can look at these. You see, this is your selenium. There's no selenium over there. So this lead selenide islands are the ones that form initially, and then they etch and they form the cesium lead bromide. But some amount of lead selenide are left over. But it does some magic. The magic it does is it does not change the absorption spectrum, but it improves the luminescence. Okay. So this is one such example where it improves the luminescence quantum yield from 50 to 90%. The magic it does is improves the PL stability with time. These are the ones with lead selenide. This is the one without lead selenide. It also improves water stability with time. Okay, and with the amount of water and with time. So when you do not have lead selenide, this just degrades very quickly. Okay. I'll not go into the theoretical details now, but this is also possible not just in the cesium lead bromide, but with iodide and iodide bromide, which are the two materials that have been used for solar cell applications. And why this is happening is because, you know, uh, you do some another experiment where you take a film of cesium lead bromide and coat another film of cesium lead iodide. Okay. So bromide film, coat iodide film on top. And this is what happens. This is your bromide emission, green. This is your iodide emission, red. But you put one film on top of other, and what you see is an orange emission. Okay. It corresponds to CSPBBR 1.5, I 1.5. Okay. But when you have lead selenide, whether it is coming from molybdenum or from the selenium precursor, you see both these green and red peaks. And these peaks, they are stable for months altogether. And we could even make some white light emitting devices using these materials, because this is green and red, and then you use the blue from the LED, and you can make these white light emitting devices. Okay, what it does is that okay, maybe I show this and then tell. So we also just didn't do for selenite, but we also tried with sulfide and telluride, and saw that telluride is the one that has uh, most effect. So it's the most stable with water. What these things are providing is that you have a lot of vacancies of selenium and sulfur. Okay, and sorry, of the bromide and iodide. Okay, and because of these vacancies, all these ions start to migrate. The bromides migrate towards iodide, the iodides migrate towards bromide, and you form a homogeneous solution of bromide iodide. You plug the vacancies when you add some amount of selenium or sulfur or tellurium. The moment you plug these vacancies, these iodide or bromide cannot move. And the other thing is that bromides and iodides happen to be ionic in nature, much like sodium chloride, salt. This is also a salt which is ionic in nature. Selenide or sulfide, when you put, or telluride, when you put, that is more covalent in nature. And if you put some covalent thing, then it becomes also stable. And the covalency increases down the group. So tellurium is more covalent than selenide, is more covalent than sulfide. And you see tellurium, the lead telluride is the one that stabilizes it most. Okay. So this is pretty much that I think I wanted to tell you about these transition metal dichalcogenides, that they're a very versatile kind of materials, where we can also make a lot of heterostructures. And we can use them for diverse applications, as you've seen for optoelectronics or electrocatalysis. Of course, molybdenum sulfide and all these materials have been known for ages for lubricating materials, the bulk materials. But now with the uh, nanomaterials or the 2D materials, you can do a lot more applications as well. And also, we happen to stumble upon perovskites, uh, just by working with these transition metal dichalcogenides. And we could also stabilize these perovskites. So, thank you so much for your kind attention, and I'll be happy to take some questions now.
Thank you, Samir sir. There are some questions.
Sorry?
So, I can read from Dr. PB Rajeshwari.
Yeah, I'll open the chat box also.
What differences are there in terms of functionalities for transition metal dichalcogenides with respect to vaccines?
So, a lot of vaccines, in fact, vaccines are even more stable. One thing, because what you're dealing with is carbides over there, right? The
Oh,
functionalities are, if you look at broadly, if you look, and the functionalities are similar, but you can add on a lot more functional groups on either of these materials. Okay. But the stability is much higher for vaccines.
okay. So the next question is slightly, uh, he feel these are all lab level development. Where do we use in material conversation quantum domain? Actually, I think I can comment here
Hmm.
because these materials they were discussed earlier, but not grown using chemical route. Uh, those are all actually having quantum nature and they are being considered as quantum materials. certainly not all the phases, depending upon the in what symmetry and in which structure we make MOSE2 or MOS2 and WSE2, WS2, they show some topological protection.
Topological. These are topological
So
insulators.
yeah, so these materials are very much in quantum domain. And the next query I think you can address, will we be able to use these materials by engineering them to custom requirements? So basically, I can assist you. Dr. Lakshmi Narasimha Rao, he is from ISRO Bangalore. So he must be thinking of producing these materials in bulk and utilizing them for some large scale requirements.
Uh, See, the way we do these, we are not producing them in bulk. But I did have a project with ISRO. In fact, even now, some of the SSE members from ISRO are interested. The photo detectors that we made, I did not show you the results of the other photo detectors. We enhanced the range to NIR and MWIR regions. So that is your um, range where you do a lot of radar detection. So we did. So one of the companies that I showed, Analinear, they make these cameras, and we made single pixel detectors using the transition metal dichalcogenide based systems. So ISRO does have a lot of use for these. But yeah, I mean, we make them chemically. I don't think it's a big issue to make these systems or
Yeah,
produce them
maybe
in
later on
larger
we can
quantities.
scale it up. Yeah. Okay. There's one more query from him. How about the developments of these materials across the globe? Uh, Sorry, sir. I think we lost your voice again. Let me try. Hello. Sir, we lost your voice again. Yeah, yeah. But okay. Anyway, so I think we are winding it up. It's okay. So let me try if I can. Uh, you can put it on speaker. Okay. So supposed to be now it should be audible. Yeah, you're audible. I'm audible, hello, but apart from the phone, can this participants be can hear you? I'm not sure. If you put your phone on speaker, then I think the participants will also. Okay, both are fine. Yeah. So you were explaining how about the developments of these materials across the globe. Yeah, I mean, a lot of people are working on this. So I do not know if this question is. Yeah. So is this a question? I mean, meant for that or something else is being asked? I can connect it that these materials are being explored across the globe. I think since last uh, 5 to 10 years, I saw. I think 2009. 2009 is when they made the first molybdenum sulfide. 2008 or 9. Yeah. are being investigated throughout the for
Quite a lot of research going on.
And is this catalytic for H2O decomposition for H generation? I think this was the case.
No, so I don't know if this is Dr. Prahlada Rao.
Yeah.
I see that question. And so we are not decomposing water. So what we do is we split. So this is called water splitting. Well, since we have plenty of water, we want to make fuel out of it. So, and hydrogen is a clean fuel. What you do is you split water, you make hydrogen, you make oxygen, you burn hydrogen to get back water. So that's what the idea is.
Yeah, for me, sir, it's really nice. But uh, when we play around with the defects, actually the sort of defects you uh, highlighted, they are very ordered defects. So suppose we have one ordered defect and our own material, and at the defect boundary, there must be some, uh, definitely there is a structural symmetry breaking, and there should be also some electronic structure kind of thing. So change in the electronic structure, local density of states kind of thing. So can you comment how it is helpful or when it can be utilized for different applications?
Yeah. So when you have these defects, remember these are, as you said, these are local traps, defect states or traps. If you're looking at, for example, fluorescence in these moons, that one is not a very highly fluorescent material. It's or molybdenum sulfide for that one. These are, but if you look at the fluorescence gets quenched because of these traps. Because these traps are the ones that they trap the charge carrier, right? At the same time, if you're looking at some of the conduction processes, again, the charge carriers get trapped. But so these are rather adverse effects. But if you're looking at site, because the fact that these defects, they leave some dangling bonds, some unsatisfied valencies, as you say. They are hungry for some atoms to come. So catalysis is very good. If you think of a very ideal 2D material, then on the top and the bottom, it's completely satisfied. Valencies are completely satisfied. It's only at the edges that you have unsatisfied. So only your edges are the reactive places. But if you have a lot of defects on the top or bottom, whatever, in the plane, then those sites also become activated. So your catalytic activity would enhance.
I have one more small doubt or query, you can say. I have one MOS2 sheet and another MOS2 sheet, and literally they are joined together along certain direction. Okay, but since we have different directions, we should see different band gaps at the interface. So, do they make kind of heterojunction at that interface? They are both same material, only there is a twinning kind of thing. It's a rotated one.
Absolutely. In fact, I'm not an expert on that, but I have seen these papers. Um, they even twist like the twisted graphenes.
Yes.
It, there's a lot of work by one Monish Chawalla. He has done a lot of work on these materials. Uh, he's also worked on twisted graphenes also, but also on these materials where he has made these heterostructures. So to make these heterostructures, you need MB kind of experiments, right? With our chemical methods, you can't do that. He has done these, and these are a lot of physics involved, which you know is way above my understanding.
Not like that, but yeah, this is interesting to see a small change in the direction makes fascinating results.
But there are very interesting results out there.
So there is one more query from one of our participant, UC Bin. Sir.
Yeah. So DLC or pseudo capacitive, actually, I think I have not included those results over here. I've just shown the capacitor behavior. Let me see if so the EDLC and the supercapacitive fractions are not given in this, but it's there in the paper. This paper was published last year. Yeah, I could quickly see it and tell you, but see this qualitatively speaking, cobalt 2 plus cobalt 3 plus equilibrium is also there. So there's a lot of pseudo-capacitive nature as well. But exactly what is the percent that is there reported in the paper? I don't remember it in my head.
Yes, sir. I think we can refer to the paper. So with this, I think I would like to thank you once again for kindly agreeing to deliver the lecture. I know you have been working in such class of material since long time, and your expertise are really useful for our own understanding. So thank you, sir, once again. Thank you for taking your time and for this lecture.
Thank you for inviting me to this August gathering and allowing me to present my results. Thank you so much, Manoj.
Thank you. Thank you.
I'll leave now.
Yes, sir. Please. Thank you, sir.